Okay, one more problem from this section and then we're going to stop. So this is a group problem, so I'm going to make you go off and do it on your own. You know, find your little robot to help you. If you've got a general purpose artificial intelligence, you know, that you've been training on your computer, you can use that one to help you too. So let's try to figure it out. So we know that member AB is rotating with an angular velocity of 4 radians per second and an angular acceleration of 5 radians per second squared in the directions that are shown. We want to find the velocity and acceleration of the slider block C. We know what direction that acceleration is going to be. We also know what direction that velocity is going to be, but we don't know its values. So how are we going to do it? We're going to follow the solution procedure. Also, note that point B is rotating about point A, so that will help you out there to solve everything else. So with that being said, I'm going to stop here. You're going to go off and try it on your own. And 3, 2, 1, and you're done. So since point B is rotating around point A, well, its velocity is going to be easy to find. It's going to just have a tangential component, and its acceleration is going to have a tangential and a normal component. And we can solve for all of that using what's given in the problem statement. The normal component is the angular velocity squared times the position vector. The velocity is just the angular velocity times the position vector. And the tangential component of acceleration is the angular acceleration times the position vector. We plug all of this in, and we have all the components we're going to need. This is going to be helpful because we can now solve for the acceleration and velocity of point C using our relative velocity equations. Now, you could very well try to find an instantaneous center of zero velocity if you wanted to. That would probably work fairly well, but it might not be all that simple. Let's see. Okay, velocity going that direction. Actually, it'll be over here. So there's my instantaneous center of zero velocity, somewhere over here. And if you want to, you can do that. However, it might be easier in this case to just use our relative velocity equation. So we plug everything in here. We're very, very careful with our cross product. And we get an equation. If you're wondering where this came from, it's because we have this little slope triangle here to help us out. So, with that in mind, we have two equations, because we equate the I and the j components, two unknowns, and while I hate to do it, we have some algebra. So we solve, and we get that the angular velocity of BC will be 3 radians per second, and the velocity of point C will be 2.5 meters per second. But it also asks for the angular acceleration, so we'll have to do our relative acceleration equations now. So the acceleration of C, which we know what direction it is right here, just don't know its magnitude, and the acceleration of B, which we know its direction and magnitude. Then we're going to have our tangential and normal components for B. So that'll be the angular acceleration of BC, which we need to solve for, and the angular velocity, which we just solved for. We plug it all in, and we get an equation that has I and j components. So we equate all those, two equations, two unknowns, and we can solve. What do we get? We get that the angular acceleration will be 12.4 radians per second squared, and the acceleration will be 13 meters per second squared. Okay, so that is it for this time. Thank you all for listening. I hope that helped you. Those relative velocity and relative acceleration equations, we've been using them all semester. We've been using them in different ways, but they just keep on coming back over and over and over again. So hopefully you haven't forgotten them. Hopefully this has helped to review that if you had. And I look forward to seeing you all next time. Have a wonderful day. Bye-bye.